And this is joint work with Karim Eldefrawy and Nathan Manohar. So a homomorphic encryption scheme, it's a normal, say, public key encryption scheme, except it has another functionality, evaluation. And what this allows me to do, say maybe as a computationally weak client, I can offload my data to the cloud in an encrypted form. And then when I want to, I can tell the cloud server to evaluate some function on the ciphertext using this evaluation function. And what is surprising about this is that the cloud can do it despite the ciphertext looking like nonsense. So it doesn't have secret key material, it just has public key material, and it can come up with a ciphertext encrypting the right value. So encrypting a function, the function I requested, on the messages. So here, F can be many things. It can be a medical diagnosis, a classifier, an inference function. And we say a scheme is fully homomorphic, or FHE, if F can be any efficiently computable function. And also, the decryption circuit doesn't change. The decryption algorithm, the complexity of decryption, is the same before and after evaluation. So FHE was proposed as a challenge in the late 1970s, but it wasn't until 2009 when Craig Gentry, then a PhD student at Stanford, came up with the first plausible construction using ideal lattices. And the intuition behind why lattice-based schemes are good for FHE is that these schemes are noisy, so there's some underlying noise value in the ciphertext. And as we compute, this noise grows. But if the noise gets too large and it wraps around, say, the ciphertext modulus, we can no longer properly decrypt. So we have to somehow homomorphically denoise the ciphertext. And the way we do that is through something called bootstrapping. And this is where we run the decryption algorithm homomorphically in order to lower the noise. And an important intuition here is that in lattice-based schemes, the decryption algorithm is pretty simple. It's always a linear part followed by a rounding part. So this simple decryption algorithm enables bootstrapping in a way. So we can bootstrap, lower the noise, and continue computing. So there are three main lattice-based schemes, FHE families. So the first is BFV and BGV. These are named after their authors. And these BGV and BFV, they encrypt high-dimensional vectors of integers modulo p for some plain text prime or power of prime p, where p is maybe 20 or 30 bits. And the important part about these schemes is that they enable arithmetic computation. So you can do a ciphertext multiplication, and the resulting ciphertext will encrypt maybe, say, for a Hadamard product or an entry-wise multiplication mod p. Same for addition, and also important for applications, you can homomorphically rotate these ciphertexts. So if you want to do something like an inner product or some linear algebra, you have to rotate them. And also, so the dimensions here are, so the plain text vector is in the thousands often. CKKS is very similar in terms of runtime, parameter size, and ciphertext size, except that the key difference here is that instead of integers modulo p, they encrypt some form of floating point arithmetic, or real or complex numbers. So whereas before you always knew you would, in each ciphertext slot or each plain text slot, you have exactly log p bits of precision. In CKKS, the noise eats away at the low order bits of the message. So you also have this, this parameter called bits of precision that you have to track throughout the computation. There's also few in TFHE. These schemes are more lightweight. They encrypt a bit or a small number per each ciphertext. The bootstrapping is much faster, but you have to bootstrap basically every nonlinear operation. So they're more lightweight, but the overhead is higher. But in this talk, I'll be mostly focused on BGV, BFE, and CKKS. Some important applications for the first set of schemes: PSI, PIR. There's a lot of interesting work in CKKS going on right now with PPML, as you would imagine. Yeah. So something that's important, though, is that in these SIMD schemes, you only have polynomial arithmetic. So in the PPML setting, if you want to do like a ReLU or a comparison in CKKS, you have to do a high degree approximation. OK. So because of these different functionalities, there are some reasons why you'd want to switch, say maybe homomorphically on the server, between different schemes. Say maybe you have a hardware accelerator for really specialized for one type of scheme, or maybe like a bootstrapping accelerator. You can homomorphically switch, bootstrap, and homomorphically switch back. So this would save cost. And then there's always the case of the ReLU example, right? So something that's done often is that you do a PPML computation using CKKS, and then you would homomorphically switch to FHE or TFHE, do this comparison or ReLU, and homomorphically switch back. But that still requires some form of bootstrapping. So one way to switch is that you can use, say, CKKS for everything, but you have to do a high degree approximation for comparison. So this is somewhat inefficient. You can break the client-server model, so you could send everything back to the client, have it decrypt and re-encrypt back. But once you start doing this, the question arises, why not just have the client do everything? So this kind of breaks the motivation for FHE. We know how to switch between all these schemes using bootstrapping, but in terms of practicality, bootstrapping is the least efficient computation you have to do in FHE, so it's best to avoid it, especially for applications. And so one thing people have been looking at is how to do this scheme switching without bootstrapping. And that's what we're going to talk about throughout the rest of the talk. OK. So before I keep going, I want to show what is, say, a BGV ciphertext, because I'm going to use the same terminology throughout the rest of the talk. And these pictures come up often in FHE, and this is something that we should all have in our minds, is say we have this bar representing all the bits of the ciphertext modulus. Where does the plaintext live, and where does the error live? So in BGV, the message is in the low order bits on the right. The error is right above it. And then everything else above that is zeros. But as the computation grows, this modulus noise gap closes. And then if it overflows, you can no longer properly decrypt. So a BGV ciphertext, it's an ROW encryption. It has two polynomials of fairly high degree. We're using cyclotomic rings often, most commonly the power of 2 cyclotomic rings. And the ciphertext modulus is some q. So the polynomial dimension, this n here, is usually in the thousands. Say 32K is a common parameter size. And this q here, or this ciphertext modulus, is usually in the hundreds or thousands also. And for efficiency reasons, we have this be a product of machine-sized primes, which we call NTT friendly. This is because in applications, you want to avoid multi-precision arithmetic if you can. If you can use ints, that's much better, or longs. And another important thing is that the number of these primes is related to the computational depth. A very easy way to control noise growth is to do something called rescaling. But as you do more ciphertext multiplications, you're actually going to end up in BGV, you're going to end up lopping off these primes to control noise growth. So in order to bootstrap, you have to raise the modulus again somehow and also homomorphically decrypt. OK. So here are simple pictures of all three SIMD FHE schemes. So I already talked about I already talked about BGV here in the middle. And BFV is up top, where also the message bits are in the high order bits, and the error, the noise modulus gap is in the middle. And then CKKS, so it's good to compare CKKS and BGV, where the message bits are in the middle, and then the noise grows, slowly eats away at the message. But you also have the modulus noise gap closing over time, too. So BGV and BFV intuitively are the same. Like they have the same plain text space, the same parameter settings, and it's known how to efficiently switch between them with just a scalar multiplication. This is something that was done maybe in 2013, and it was folklore before that. But what about, say, BGV and CKKS? So even though these schemes are fairly similar, their applications were quite different. If you remember on that slide, the applications were quite different because the plain text spaces are very different. I should also say, like, we know how to do this with bootstrapping. For example, if you take a BFV ciphertext, you can view that as a form of a CKKS ciphertext without much room to work. But can we do this without bootstrapping? And our result is that you cannot. So we show that a very simplified form of scheme switching actually immediately gives you bootstrapping. So this means that you have to go through bootstrapping every time you want to switch these schemes, which is a little unfortunate, but it's a very interesting fact. OK. So in the paper, we show both directions. We show that if you can go from CKKS to BGV, then you can bootstrap in BGV efficiently. And the other way around, you can bootstrap in CKKS efficiently. But this picture is important, right? So we're going to have, say, for the first direction, we have an input, a BGV ciphertext. We want to switch it efficiently to a CKKS ciphertext. Really what that means is that it means taking the message bits in the low order bits in BGV, putting them in the middle, and maybe you have a new error distribution for the low order bits in CKKS. And in the paper, we model this as an oracle, but it's just an algorithm. And what we show is that the intuition here is that you're actually going to treat the CKKS ciphertext at one point as a BGV ciphertext. And then this switching is going to do a significant part of the bootstrapping algorithm for you. OK. So quickly, what is CKKS bootstrapping? You're given an input ciphertext without much room to work, so the modulus noise gap is small. And then the output ciphertext is going to have a lot more room to work, but you might have maybe a little bit larger error that might eat away at the message. But this modulus noise gap is large again, and this means you can continue on with your computation. So the way that's done is that a simplified version of CKKS bootstrapping is you take the ciphertext, you mod up, treat it as something with a larger modulus. But now, if you were to decrypt, it would be useless because you'd have some wraparound mod little q. And this wraparound is small, so this polynomial I of x has small coefficients because the reason is that the secret key usually has all small coefficients. So that's step one. You have a new ciphertext in the right space, so it doesn't decrypt correctly. And if you were to try to compute, this would mess everything up. So then you do a homomorphic evaluation of the mod q function. And the way you do that is you actually approximate it, because again, you can only work with real number arithmetic. And you also do some homomorphic linear transformations where you take the polynomial's coefficients, put them in the slots, the ciphertext slots through polynomial interpolation. Do it homomorphically, which is a heavy operation. Do the mod q approximation and go back. OK, so what about doing this with switching, right? So what would a switching algorithm entail? Again, we represent this as an oracle where you have an input BGV ciphertext, you have an output CKKS ciphertext, and the only thing that matters is that the message bits are in the right space. Maybe the modulus gets smaller, maybe the noise gets larger, but in the end, as long as you have the message bits in the right space, then you're good, or in the right spot in terms of the modulus noise gap and the ciphertext modulus. So this is a simplified version of what we have in the paper. We do this with all the parameters in more detail in the paper. But again, it's really just that the message bits are in the right spot. And something that we show is that even this very simplified form of scheme switching. So we already assumed that you've done the work to homomorphically unpack, put the message bits in the right spot for say, BGV. If you just do this part of scheme switching where you don't take care of the packing, it already immediately implies bootstrapping. So this is a simplified version of scheme switching, but that actually shows that it's even harder. Okay, so this is the time when everyone should wake up, because this is the whole idea of one of the results of the paper. So I'm going to show how we do this for bootstrapping on CKKS with an oracle that switches from BGV to CKKS. And the intuition is that we're going to treat this, at one point, we're going to treat a CKKS ciphertext as a BGV ciphertext. So the way we're going to do that is we're going to do the first part of bootstrapping, which is basically a no-op, raise the modulus to the point where you have this wraparound mod Q, this little q, in the large space. But we have to clear these bits represented in I of x if we want to continue computing. And the intuition here is that this I of x, we can treat this as error in BGV. Or another way to view this as we can treat the message and the error as a higher precision message, or a message in a larger space, switch, and then we're going to rescale later on. Okay. So if you plug this into, say, an algorithm that will switch, it will shift the message and the error all the way up, a little bit more in the middle, and treat it as itself as a message with a lot of bits of precision, say. And it will also introduce this new error, E prime. But something, if you go all the way back to the BGV slide, and something we can do cheaply is we can rescale very efficiently in these schemes. So we can rescale or homomorphically lop off the bits represented by delta. And at this point, we now have a refreshed CKKS ciphertext where the only thing you lost is however many bits represented by delta, or basically one level. So if you're keeping track, it's whatever the oracle gives you minus a level, but this is done very efficiently. This is done very efficiently homomorphically. So in the paper, we do the full details of what we call weak scheme switcher, which is what we saw. And again, this weak scheme switching already immediately implies bootstrapping. And then we also did a strong version of this where you take into the accounts the polynomial interpolation, or the packing of the scheme. This is done just through homomorphic linear transformations, as you would expect. And we also see how bootstrapping relates to things like comparisons or ReLU and min and max, showing that if you can bootstrap with a few calls to these homomorphic functions, then you should also expect them to be somewhat heavy. Again, in these SIMD schemes where you can only add and multiply homomorphically. So yeah, the conclusion is that switching, even though you can switch for free in BGV and BFV, switching between these schemes and CKKS is actually quite powerful. So that means that you really have to go through bootstrapping in your applications if you want to switch mid-computation. Okay, thank you. Any questions?
Any questions, please? So if not, maybe I can ask.
Yeah.
So my question is, what's the switching's impact on the errors? Is it possible you have overflow sometime?
Yeah. So, what's the scheme switching on the error, right? We model this as whatever the algorithm gives you. So if it blows up the error, then that would be a poor scheme switcher. If it gives you a nice error, then that would be a good scheme switcher. But the impact is that you have to do a rescaling after. So it's really how well can you do this, right? And you can plug in bootstrapping for that algorithm, and it would give you a pretty good error. But it would be, in terms of practical applications, it would be quite long. So for example, common BGV or CKKS bootstrapping takes a few minutes.
Yes.
Yeah, so something like that.
There's one more question. Sorry. So you talk about the switching between the first two. How about the TFHE?
Yeah, that's a good question. Yeah, so switching between, let's say, TFHE and FHE and, say, BGV or CKKS, we can do that, but it involves these homomorphic linear transformations, which are a heavy part of bootstrapping. So it is in itself bootstrapping right away. Yeah.
Hello. All right. Yeah. So CKKS sort of is generally, I've seen it defined like there is no error in some sense. Is this?
Right.
Like,
yeah. So part of CKKS is where they treat the error as and message as the same, right? And then this causes some security issues if you publish.
Yeah.
Our work is orthogonal to that, and in applications you would actually track your message bits and your error bits, because you have to know how many bits of precision you're getting.
Right.
So that's what we do in the paper.
So that's what you're doing in the paper?
That's what we do.
Like that? Okay.
Yeah, because if you look at some CKKS papers, you'll just see M of X, right? And
I mean, yeah, and that was sort of the idea. I mean, that was the idea behind CKKS. They made it different than BFV.
Exactly, yeah. But in applications, you should really track the noise growth so you know at what point the message bits are useless, right? Yeah.
So if we do not have any questions, so let's thank the speaker again, please.